Hey everybody, and welcome to another tutorial. I'm Brad. I'm the creator of Expanse, the volumetric cloud, sky, and atmosphere plugin for Unity's high-definition render pipeline. And today we're going to be talking about how you go about using Expanse to model the Earth's atmosphere. And I promise that if you stick around for the whole time, I will also show you how to model Mars's atmosphere and get some visual results, kind of like you would see with the Curiosity rover photos with the blue sunset and everything. So, without further ado, let's jump in. So before we dive into Unity and we start futzing around with different sliders and stuff, I want to give a little bit of a theoretical overview of Expanse's atmosphere model. And I think that by doing this, you're going to have a better understanding of what all the parameters mean, and you're going to be way better equipped to go and build your own custom cool alien atmospheres that are different and even more interesting than just Earth's atmosphere. So, there's not going to be any math involved. It's not going to be very technical, right? I'm just going to try and give an intuitive explanation of the different components of the atmospheric model so that you can go off and build your own atmospheres with confidence. So when we're talking about constructing a model of the Earth's atmosphere, we first got to kind of think about what our goal is. And for us, the goal is to get a really cool, pleasing visual result. So, we're not trying to simulate the weather. We're not trying to, design a spacecraft that's going to fly through the atmosphere. We mostly just care about how it looks visually, and we care mostly about how light interacts with it. Because light is the thing that ultimately we see, right? So we have to ask the question, the most fundamental question when we're starting to model any natural phenomenon. What is it? We have kind of an intuitive understanding of what the atmosphere is, right? At the end of the day, we know we want to end up with some kind of blue gradient, that looks like the sky. But we're going to have to formalize our understanding a little bit more in order to construct a visually convincing model. The first component of the atmosphere that we're going to talk about is what I'm going to call gas. Gas is sort of a bunch of, little molecule particles, right, that are suspended in the air. For Earth, this is a combination of nitrogen and oxygen and other gases, like, you're probably familiar with carbon dioxide because it gets talked about with global warming so much. And this is sort of one category of stuff that makes up the atmosphere. And they're all categorized together because, these different molecules behave similarly in terms of the way that light interacts with them. Another category of stuff in the atmosphere is dust and smoke, or what we would call aerosols in the atmospheric scattering literature. And these are sort of responsible for the look of smog around a city, or like the look of pollen floating around in a forest, and sort of the haze that you see around the sun disk on a really like foggy day. And then finally, there is water in the sky, and they are what you would probably recognize as clouds. Clouds are just droplets of water that have been either condensed around dust particles or have frozen and are little ice crystals that move around. So these are the different things that make up the atmosphere, and something that we can notice that might seem kind of obvious, but it's important for when we talk about how to render the sky, is that all these things are fluids. They're gas, and they're liquid water, right? Droplets. And this is fundamentally different from what we usually talk about in computer graphics. We're talking about surfaces, right? Usually we think, okay, if I'm going to model something, I'm going to open up Maya, I'm going to, create a triangle mesh, I'm going to extrude some stuff, and I'm going to add subdivision surface modifiers, and at the end of the day, what I'm going to have is a surface that has a material on it, right? But when we're talking about fluids, we're talking about something that's totally different. We're talking about a volume of tiny particles that are arranged in kind of a 3D shape, right? We're no longer talking about a surface and a material. We're talking about a bunch of particles in sort of a particular pattern. And this has huge ramifications for how we render it, because when light interacts with the surface, it just bounces off, right? And that's all we really need to worry about. But when light interacts with a volume of a bunch of different little particles, light bounces off of all these little particles. And it bounces off and scatters in different directions. And there's tons of tiny little interactions that happen as light passes through a volume, through a fluid. So, one possible strategy that we could use is we could just say, well, hey, this looks familiar, right? All those little particles, they're just little surfaces. So we can just simulate each little particle, give it a material, and then just bounce light around off of all of those little particles and render each one individually. And if we do it correctly, it should look great, right? You might be able to get away with this in an offline renderer. I've seen some papers around what are called particle-based volumetric rendering methods, but we just do not have the cycles to do this. This is way, way too inefficient for us. So instead, we're going to come up with a statistical description of the volume of particles. We're not going to simulate each particle. Instead, we're going to think more about the particles as kind of like, we're going to not think about the particles at all, really. We're just going to come up with a way to describe the particles that's more efficient, and then we're going to render using math. We're not going to render each one individually. So you might wonder what I'm talking about when I say a statistical description. We're going to have a 3D texture or a mathematical function that tells us where in the volume particles are and where they aren't. So we're not actually going to come up with the positions and orientations of billions of particles. Instead, we're just going to have sort of a cheap lookup function or a texture that says, hey, I don't know exactly where the particles are, but I know that there's a lot of them right here, or I know that there's not very many of them over here. And we're going to call this object the density field. And this is basically, it's going to tell us, at this spot, there's a high particle density. There's lots of particles smushed into this area. And in this spot, there's a low particle density. There's not many particles at all. And this will allow us to, this is just a much more efficient representation because we can control the resolution of this density field, or in our case, we can come up with simple mathematical functions that describe the density field. And we don't have to simulate billions of particles. We can just simulate a couple of cells of particles, or a continuous function that takes a couple parameters. Here's an example of a really high resolution density field that's a texture density field. We're not going to be working with anything that's complicated. I mean, that looks like it could be it looks kind of like those pictures that you see on clickbaity articles that are like, this is a model of the whole universe. We're not going to do anything like that, but this will kind of give you a feel for, these sort of colored areas here are spots where there's lots of particles, and then the transparent areas are spots where there aren't particles. So the density field is very powerful, right? It's a good description of where there are particles and where there aren't, and it lets us abstract away, the positions and locations and the amount of particles that there are. But this can't really be the whole story. I mean, there's sort of a big qualitative difference between smoke and sky, between those two sorts of volumes, independent of just how much of it there is, right? And we're going to chalk this up to something, stuff we're going to call molecular properties. So the density field isn't the only thing. It's not the whole story. There are properties of each individual particle in the gas that determine how light interacts with them on a microscopic level. And while we're not going to care about simulating light bouncing off of each individual particle, we will need to come up with some description of these molecular properties that will allow us to differentiate something like smoke from something like the atmosphere. So the easiest way to think about this is to think about what happens to a light beam as it interacts with an individual particle. The basic interaction, at least one interaction that we can think of, is that light's going to come in it's going to come into the vicinity of this particle. Some physics magic is going to happen, and then it's going to get scattered off in some other direction. It's going to come in, and then its direction is going to get changed, and then it's going to go off in some other direction. So this naturally we call scattering. But this is only one behavior that light can have when it's interacting with the particle. Another thing that can happen is that light can come in, physics magic can happen, and then that light can just get absorbed by the particle and converted to heat energy. And this is fittingly called absorption. There's one other point that I want to make about scattering and absorption, which is that if we have white light coming into the particle, we could possibly have red light coming out. And this is because the scattering properties of the particle, the molecular scattering properties, could be wavelength dependent. So red light could interact with the particle in a way that's different than blue light, right? And in fact, these molecular properties of the particles, these wavelength dependent molecular properties, are what cause the sky to be blue. Red light interacts with the gases in the sky in a way that's different than blue light does. So we sort of know what we want to do. We need to have something that is wavelength dependent, right? That can model absorption, so light getting attenuated, and can model scattering, so light getting kind of reflected around the volume. And we're going to do this with two sets of numbers: the extinction coefficients and the scattering coefficients. These are both RGB colors, and the extinction coefficients tell us what color of light gets absorbed, and the scattering coefficients tell us what color of light gets scattered by the volume. Just remember that these are not really the truth. They're not really a super great physical model. They're just simple stand-ins for more complicated sort of reductionist molecular properties of the gas, but they're going to work great for us as 3D artists because they're going to give us a great amount of control, sort of intuitive control, to get the gas looking how we want it to look. So here's an example of a volume of gas rendered with yellow extinction coefficients and no scattering coefficients. And you might be surprised because the gas is blue, right? But the extinction coefficients are yellow. But what does a yellow extinction coefficient tell us? Well, yellow is a mix of red and green, and the extinction coefficient tells us what kind of light the volume absorbs. The red light is going to get absorbed. It's not going to make it through. The green light's also going to get absorbed and not make it through. And only the blue light is going to come out and eventually hit the camera. So a yellow extinction coefficient actually produces a blue volume. Now, if we add in some red scattering, we can see that this looks very different, right? The edges of the volume are red. But then as we have to start going through more material, more light starts to get absorbed as opposed to scattered, and we start to see it become a blend of blue and red. We get something that's kind of purple, kind of purplish pink. So there's another natural question that we can ask when we're thinking about how light scatters off of an individual particle. And that is that we have light that comes in, some physics magic happens, and it leaves in some direction. And we can ask the question, is there any relationship between the direction that light comes in and the direction that light goes out? Is it the same direction? Is it a different direction? Is it a random direction maybe? And there are different behaviors that we're going to want to model here. And this notion of there being a relationship between the input direction of light and the output direction of light is what's known as the phase function. So one case is isotropic phase, and this basically says for all of the different input directions, the output direction is just random. It doesn't matter what input direction you're coming in, you're going to go out in some other random direction. And the other case that we're going to care about is called directional phase. And for directional phase, you're going to have light coming in from all sorts of different directions, and it's all going to leave in roughly the same direction. And there's, in fact, all components of the atmosphere have some amount of directionality to their phase function like this. So here's an example rendered in Expanse. You can see on the left we have some sort of smog, smoke type thing that's rendered with a less directional phase function. So it's sort of spread out very wide around the sun disk. And then on the right-hand side, we have that same smoke, smog, rendered with a more directional phase function, and it's concentrated in a way that's way tighter around the sun disk. So it has a strongly preferred direction that it scatters in. It likes to scatter in the direction of the sun. All right, so that is our full model of a volume of gas. We have our statistical model. We have our density field, which tells us where particles are and where they aren't. And then we have the molecular properties that differentiate something like the sky from a plume of smoke. They're the extinction coefficients, which tell us what color of light gets absorbed by the gas. There's the scattering coefficients, and they tell us what color of light gets reflected by the gas. And then we have the phase function, which tells us if there's a preferred direction that the light likes to scatter in when it goes through the gas. So now we're going to jump over to Unity and see how all of this shakes out when we actually try to do it. For a detailed overview of some of the stuff that I talked about in this presentation, I'm going to put a link in the description to Pixar's production volume rendering course. It's a really, really good sort of 90-page PDF that if you're interested in this kind of stuff and if you're interested in the math behind it, you can read, and you'll have a really solid foundational you'll have a really solid foundation for exploring more volumetric rendering techniques. But for now, let's head over to Unity and get started with that. All right, first I'm actually going to take a pear break. Oh, it's a good pear. I feel like pears are the least appreciated fruit. They always get sidelined for apples, but I think they're better. I think they're better than apples. All right, so here we are. I've got Unity open. This is a sort of empty HDRP project, except I've made a couple small modifications. The most obvious one is that I've imported this model of Lower Manhattan. I'll put a link in the description to where you can download this model if you don't have a cooler 3D model that you want to use. I like this one because it's pretty big, and which means that you'll be able to see the effect of fog, and you'll be able to see volumetric shadows really well. I've also got the main camera positioned in a spot that I like, and I've also deleted the default directional light, and then I added a global volume with a couple of overrides on it, and you'll want to sort of do this as well, just to make sure that you don't have any problems. One of these overrides is the exposure, which I have set to automatic. And I've got the minimum at 7 and the maximum at 12. You can tweak this to look how you want, but I like these numbers. I've turned off bloom. I've also turned off Unity's default fog. And I have set the max shadow distance with the shadows override to 5,000. And then I've actually done one more thing, which is I've adjusted the clipping plane of the camera, the scene camera, to be 200,000, so very far away, and the main camera to also be 200,000. And the reason I do this is because Expanse computes fog out to a certain distance, and that distance is determined by the far clipping plane. So you're going to want to set it to some value that's pretty high. That way you don't get fog artificially ending too early. All right, so now our scene is all ready to go. By the way, if you haven't watched the Getting Started tutorial, I would recommend watching that. Because, there's some sort of fundamental stuff like how to import Expanse into your project, etc., that is going to be covered in that. And you might want to watch that before you watch the rest of this tutorial. So we're going to navigate over to the Project tab. We're going to open up the Expanse folder, and then we're going to go to the Prefabs folder, and then the Full Skies folder. And we're going to grab the Expanse Cloudless Sky prefab, and we're going to drag that into our scene. And great, now we have a sky. And we're going to go ahead and we're going to right-click Expanse Cloudless Sky in the game object hierarchy. We're going to go to Prefab and click Unpack Completely. And this will now let us make changes to this prefab. And then we're going to click Earth Atmosphere, which has all the information for modeling the atmosphere. And we are going to delete it, because we're going to do that ourselves. Where we're not going to let Expanse do it for us. We're going to do it on our own so that we can understand how it works. And now you'll see, we can see the stars, we can see the sun, and we can see the planet, but there's no blue sky anymore. So the first thing that we're going to want to do is we're actually just going to want to go ahead and create that game object again. We're going to right-click, go to Create Empty, and we're going to call it, I'm going to call it Atmosphere. You can call it whatever you want, call it Pear. Okay, I'm going to drag that underneath this. And I am going to create my first atmosphere layer. And the way I'm going to do that is I'm going to click Add Component, and I'm going to type Atmosphere Layer Block. And I'm going to click that. And what the atmosphere layer block does is it creates a density field for a particular atmosphere layer or a particular component of the atmosphere. And then it lets you tweak the extinction, scattering coefficients, and the phase function for that density field. And then it renders it on the screen for you. So it basically is kind of like, you can think of an atmosphere layer block as representing sort of one part of the atmosphere, one type of gas, type of volumetric data in the atmosphere, type of fluid. So the first thing that we have to do to actually start using this thing is we have to grab our sky and fog volume, and we're going to drag it over into the volume slot right here on the block. And now, if we uncheck it, and then check it again to reset it, you'll see we have our blue sky back. And this is because, by default, the atmosphere layer block is set up to simulate the gas component of the atmosphere. So it simulates the blue sky for you. But we can still go through and play around with the parameters to see what they do. For one thing, the name right now is default layer name. I'm just going to call it gas. This is just sort of for your own reference. It'll be used in debug printouts. And then we can go down here and we can see we've got 3 parameters that are related to the density field. We have the density. If we adjust that, that'll control sort of the base amount of atmosphere that there is, and we can get some pretty crazy results if we bump that way up. You start to get some really bad artifacts if you bump it like crazily high, and this is because you'll need to up your sample count. Or we can have none, in which case we're back to just being on the moon. And we're going to set it to 1, which is the right value for the Earth, for the scattering coefficients we've chosen. The other setting that we have that it lets us control this is thickness. This tells us how far the gas extends up into the atmosphere, away from the planet. So we can pull this down, and you can see we can kind of have a thin atmosphere layer, can be really thin, or we can, if we want to, make it super thick and get sort of a crazier looking, less realistic, but kind of interesting atmosphere. We're going to leave it at the value it was at. It's going to be 8,000. This is a good value for the Earth. And then the density distribution, this is going to tell us, how, sort of what shape the density is going to take as it goes from, the density field's going to take as it goes from the ground up to the sky. And what exponential means is that it's going to decrease as it goes from the ground up to the sky. Most of the gas, most of the density is concentrated down by the ground, and less of it is concentrated up towards space. And this is how it works in real life, roughly, right? There's more gas down at the ground because the gravitational force is stronger down there, and then as you get further away from the Earth, the gravitational force is weaker, so there's less gas up there. It all gets pulled down. Cool. So that's the density field. That's how we model the density field. And then the next thing we can play around with is the extinction and scattering coefficients. So if we go over here and we go into HSV mode, we can change the hue of the extinction coefficients, and we'll get different looks. So we can get kind of cool, interesting things. We can change the saturation too, and that'll, sort of adjust things. It'll make it paler or darker. I'm going to leave this where it was at 82 and I think 223. And then we can go to the scattering coefficients and do the same thing. And this will be more dramatic because the scattering coefficients are going to control the light that's reflected as opposed to just the light that's absorbed. And we can adjust the saturation here too. So if we want to make our sky, bluer, we can saturate it more, and it'll give us kind of even up to like a really comically saturated blue. But I'm going to leave it at 82. and 223. And then the other thing that we can do to affect the color of the sky is we can use this tint parameter here, and we can tint the sky with different colors. So if we're in HSV mode again here, and we make the tint orange and saturate it, and you'll see we get kind of like a yellow sky, and we can go crazy with it, make a disco party. I would recommend against using this tint parameter if you can. I would use the coefficients instead, because the coefficients are going to give you a result that's much more physically based. The tint is possibly non-physical. Of course, it's there if you want to use it, but I think that I just personally think it looks better and looks cooler when things are closer, or sort of have a grounding in the way that they actually work in reality when they're physically based. And then the sort of final thing to address here is the phase function parameter. So right now we're on the Rayleigh phase function, and this is the sort of correct phase function to be using for the gas component of the sky. And then if we switch this to the isotropic phase function, which has no directionality, then you can see we lose that halo around the sun. So with the Rayleigh phase function, we have sort of a little bit of a bright, wide halo around the sun. And with the isotropic phase function, we lose that. And it doesn't look bad, but it's not quite right. Okay, great. So now we have our air layer. And the next thing we're going to do is we're going to create the aerosol layer. So this is going to be sort of the dust and smog that's in the sky. And when you're creating the aerosol layer, it's good to have a reference photo to use, because the conditions, sort of the amount of dust in the sky, the amount of pollen or smoke, smog, it's going to change a lot depending on where you are in the world. And if you're trying to reproduce a particular place, then it's helpful to have some photos to look at. So I'm going to quickly pull up some reference photos. Reference. And I think the one that I want to use is this photo of Dubai at twilight. I think this photo looks so cool because you kind of have this bright blue sky up here, right? That's very pure and kind of clean. And then down here you have this sort of dirty looking smog, right? And it really highlights, it's sort of this cool balance between something very man-made and sort of dingy and the city, right? And then up above you have kind of the ethereal natural blue color, which I think is cool. Looking at some other references of Dubai, here's a sunset photo, and you can see we get these cool sort of volumetric shadows happening, these streaky God rays. And then here's a picture of it during the day. So during the day we still kind of want to have this nice blue color. There's a little bit of darkening down here due to the aerosols, but it's not crazy. All right, so we are going to go over to our atmosphere game object, and we're going to add another atmosphere layer block. Atmosphere layer block. And I'm going to call this one aerosols, and I'm going to drag over the sky and fog volume to hook it up to Expanse. And now if I reset it by unchecking and checking it again, you'll see that I now have a second air layer that's going to make the sky even brighter and even bluer. And this is not what we want. So I'm going to go down to the density distribution here. Exponential is fine if you want to use it. But I want to be able to get those cool volumetric shadows from the from the buildings, right? I want to be able to see these cool streaky shadows. And so I'm actually going to choose the screen space height fog distribution. And all of the density distributions that are called screen space, I mean, there's only 4 right now. Maybe there'll be more in the future. But the screen space ones support these volumetric shadows. They can test against the light's shadow map or the depth buffer, whichever you choose to render these shadows. So I'm going to click screen space height fog. And you can see there's a slight change, right? But generally it's pretty similar. So now you see I have a density parameter, I have a thickness parameter, and then I also have a radius parameter that controls how far the fog extends around the player. And I'm going to set this to like 10,000. And I think we'll play with these once we get the coefficients set up. So, smog is generally gray, right? It doesn't have a color. And so I'm going to set these coefficients to both be gray. And the way I'm going to do that is I'm just going to turn the saturation all the way down for both of them. Great. And the other thing about fog is that, or smog rather, is that oftentimes it scatters less light than it absorbs. It's a little more absorptive, and this is kind of what gives it that dark, smoky look. And so I'm going to take the scattering coefficients, and I'm just going to turn the value down to maybe like 25 on them. Yeah, that's good. 25. Cool. Okay. And you can see if we actually go look at the numbers, these are relatively small. If we go to RGB01 mode, these are like E-5, right? Which is a pretty tiny number. And that's just to make it so that we can put the density in a reasonable range, like 1, 2, 3, etc. Because these are related to each other. Okay, great. So now we have some fog, or some smog. I always get those mixed up with each other, but they're pretty different. We can go to the phase function here. You can see, right, again in our reference photo, that the smog is kind of, it has a stronger effect around the sun. So we're going to want to use a directional phase function. So we are going to use the me phase function. And this will give us some control over the amount of directionality we have. Here, I think I actually need to uncheck and check it again. There you go. So we can adjust this anisotropy slider, and negative numbers will make it scatter actually in the opposite direction of the sun, and positive numbers will make it scatter in the direction of the sun. So I kind of like looking at this reference photo. Yeah, I kind of like 0.8. 0.8 looks pretty good to me. Cool. And now I'm gonna set the thickness to be something lower, because I think that it's probably a little bit too. I don't think it's gonna be the same thickness as the air layer. I think it's gonna be a little bit less. So I'm gonna go something like 2,000 to start. And now I feel like I want to up the density, because there's less gas now. Maybe to something like 4. Cool. All right, great. So now if I go over to the sun and moon game object, I can adjust the direction of the sun here, this celestial body block that says sun. And I can just pull it down in this direction, and I can start to see what this looks like. So yeah, I'm getting a pretty crazy flare right here, and then as it goes over the horizon, we get that sort of cool look. So I'm going to put it right here, like kind of right where our reference photo would be. And now I'm going to go back and I'm going to tweak these settings some more. So looking at this again, it's kind of looking to me like, this is just too bright, there's too much light being scattered, and there's not enough light being comparatively absorbed. So I'm going to go back to the scattering coefficients, and I'm going to set them down to something like 5e-6. All of them in the RGB01 section. And now I'm going to up the density even more. And that looks pretty good to me. Something like maybe like 7. And then I'm also going to up the anisotropy to 0.83, I think. And I really like the way that looks. I think that's cool. And then now, just to make sure, I'm going to go back to the sun and moon game object, and I'm going to bring this back up and just make sure that I haven't deadened the look of the sky too much. And I think it doesn't look too bad. It's a little bit dark. If we go over here and we disable this, you can see it's bluer. You know what? Maybe we have darkened it too much. All right. Let's go back. Let's change these coefficient values. This is a lot of what it is. It's you're looking at your reference, you're moving the sun around, you're trying to figure out if the changes that you're making, they look good in one direction and they look bad in another direction. And I could have just pre-programmed this whole tutorial and just given you guys the right values, but I think it's more instructive for us to walk through it together and figure out how to do it correctly. So okay, let's go to the extinction coefficients here. And let's go to 0, 1 mode. And I'm going to just set these all to something like 4e negative 6. Just some value that I pick. And I'm going to set the scattering coefficients to something less. I'm going to do 2e negative 6, so half. That looks better to me. And we still have this nice little halo around the sun, but the sky is bluer, kind of like we see in this Dubai skyline. This is a little bit bluer actually, but we'll make a change in a second that'll help with that. Cool. All right, so now let's bring the sun back down. Okay, yeah, and that looks pretty good to me. You know what I might do is I might reduce the thickness of the atmosphere of this smog layer and then make it more dense. Something like that, maybe. So thickness 1200, density 12. And now as I bring it up, the sky is still pretty blue, right? Because we're not looking up through too much fog, but then as I bring it down here, it's denser, but it's a little bit shorter, so we still get that cool look at the horizon of this, this sort of halo around the sun. Great. Okay, the last thing I'm going to do here is I want to get these cool volumetric shadows in the reference, and the way that we do that is we go over to sun and moon. We click in here, shadow map volumetric shadows for the sun object. And then we go back to the atmosphere and we go to our aerosols layer and we click geometry shadows. And now you'll see we get the cool volumetric shadows happening. And you can tweak, this parameter here called max occlusion, and this will tell you how much the shadows actually affect the scattering. I'm going to put it to something like 0.8. I think that matches the reference pretty nicely. And there we go. Yeah, so now we can play around with the light direction a little more too. And we can see that. I think that looks pretty cool. And then the other thing I want to do actually is I want to bring this over the horizon, and I just want to see how it looks compared to this. Yeah, so we're getting something there for sure. We may need to make some adjustments because this is kind of purplish. This is kind of like a grayish purple, and this is very, very blue. So we might need to go back and tweak the scattering coefficients, but I want to set another atmosphere layer up first, which is something I actually didn't talk about in the presentation, except mention it in passing, but that's actually pretty important for nailing the color of the sky, and that is the ozone. And the ozone is another sort of layer of gas that is way high up in the atmosphere that is purely absorptive. So it just absorbs light. It doesn't actually scatter light at all. And it can help to sort of, at least from an artistic standpoint, it can breathe some blue back into the sky. So once again, I'm going to click Add Component, and I'm going to add another atmosphere layer block. I'm going to drag the sky and fog volume over to it. I'm going to call this ozone. I'm going to uncheck it and check it again, and now you can see we've got another another sky layer in here. Actually looks kind of cool, I think, but we're not going to use it. And now, because the ozone is kind of like a band up high in the sky, we're not going to use the exponential distribution because that's not how the density is concentrated. The density is 0 at the ground, and then it's pretty high up around 30 kilometers above the surface, and then it dies off to 0 again. So we're actually going to use the tent density distribution, and this will allow us to specify a thickness and a height. So the height we're going to choose is the default one. It's 25,000 meters. And the thickness, we're going to choose a pretty thick thickness. That way it's kind of a wide band up at that height that dies off as we get closer to the surface and closer to space. And this is a good model for the ozone. So we're going to set the thickness to 30,000, which is a lot. And you can see this makes a pretty dramatic effect. Oh, this is a Unity error that happens with HDRP sometimes. It's the shader graph problem. All right, we got to hit play and then uncheck play, and then that'll fix it. All right, there we go. Okay. All right. So anyway, back to editing the ozone layer here. We then will have to adjust the extinction and scattering coefficients because they're different from the gas. The specific values here, I'll give them to you right now. Actually, I got to look them up. One sec. Okay, I have them now. So remember, I said the ozone is purely absorptive. It doesn't scatter anything. So the scattering coefficients, to specify there's no scattering, it's just going to be 0. There you go. 0. And for the absorption coefficients, the extinction coefficients, we're going to use the values 0.65 E negative 6, 1.88 E negative 6, and 0.085 E negative 6. And now you can see our sky is kind of a nice purple color. And we can adjust the density to bring it down. And now it's pretty clear that what we had before was almost kind of green. And as we up the density of the ozone layer, it turns purple. You can go really extreme. This looks kind of like a synth wave or something. This looks like it could be a Kavinsky cover. Or we can pull it down. And you can see if we bring the sun back up above the sky and now adjust the ozone, you can see that it actually also sort of adds a little bit of blue back into the sky if we really adjust it a lot. Of course, I think that this is too extreme. So I'm going to go for a value around 0.5. And I like that, I think. I think that looks pretty nice. All right. So now I want to take another look at our reference. Because now we've basically set up the entirety of the atmosphere. We have the 3 layers. We have the gas, we have the dust and smoke, the aerosols, the smog, and then we have the special ozone layer that helps to add some purple back into the sky. But I still feel like we're not quite hitting our reference here. We sort of have, this looks pretty good just in terms of like the way that the scattering is working, right? We have this dark band down here, and then it sort of fades up to the color of the sky here. But I don't think that this is blue enough. I kind of want that really moody blue twilight color. And the way that I'm going to do this, you can see first that if I adjust the ozone, it doesn't really give the right effect. That's just going to make it more purple, right? So I'm going to leave that at 0.5. And now I'm going to do something that's basically going to be an artistic override. It's still going to be physically based, but I'm not going to use the accurate scattering coefficients for the Earth's atmosphere anymore. So I'm going to go over to the scattering coefficients, and I am going to go to HSV mode, and I'm going to up the saturation a little bit to something like that. And now I'm going to take maybe the hue and sort of change it a little bit too, looking back at my reference. Oh. How saturated can we get without it looking really wonky? Yeah, I like that, I think. Maybe I'll actually pull the saturation down to like 92. And then the hue, I think 220. I think 223 is good. Great, and now you can see I'm a lot closer to this reference photo. It's still not perfect, right? This is still a lot bluer, but I actually think that like a lot of this is the result of sort of some crazy post-processing being applied here. You could always come into the global volume here and add a color curves override, and we can get that sort of exaggerated look if we want to. Of course, now the rest of the sky looks like ridiculous, right? So, you gotta be really careful with post-processing effects and make sure to use them in a way that's gonna be, that's gonna be conducive, that's gonna look good no matter where you're at. And by the way, now if we go and edit our and see how our sunset looks as well with the new scattering coefficients, it still looks pretty decent. It's actually, it's a little bit blue around the edges, but I think that looks kind of cool. And at daytime, it's nice and kind of this saturated blue like we're seeing in this reference photo. Oh, not that one, this one. Okay, so I like the way that this looks, right? I think this is pretty cool. What else can we do? Something else that I think would be useful is that maybe we have, a dynamic storm system and like a weather system that we want to implement in our game. And we need to be able to roll in kind of like rainy rain fog. I don't know, like some kind of like watery, misty, mysterious fog. And so we can do that with an atmosphere layer block as well, actually. So we can come over here and we can add another component, another block, drag over the volume, call this rain fog, and then set the density distribution to screen space height fog. And now set the thickness to something like 4,000, something kind of like pretty high, right? Because clouds will go up pretty high in the sky. And the radius can be something a little more local, like 10 kilometers, right? Because the weather changes quickly over the ground, right? And we can sort of come over here to the extinction coefficients, and we can make those gray, and we can make the scattering gray. We can set the phase function to be me, but we can make it less isotropic, so it's going to be a little bit less directional. And then we can start to roll in the density here. We can uncheck and check to turn it on. And then we can really start to up the density. And now you can see we have kind of like a misty rain fog. This still doesn't look quite right to me, though. I think maybe what we have to do is we want to turn down the scattering just a little bit, so sort of make it grayer. And then I think that rain fog always ends up looking a little bit blue. So I'm going to kind of add a little bit of blueness to the scattering coefficients, just to sort of get that hazy gray look. And then maybe I'll turn the anisotropy down just a little bit more. And now up the density. And there you have it. There's some rain fog for you. And so you could easily roll this in and roll this out with the density parameter by animating that. All right, great. So there you have it. We've got our model of the sky totally finished. I don't know how long it's taken. Maybe it's been half an hour. Maybe it's been an hour, 45 minutes, but here we are. We've built a mathematical model of the atmosphere. We've rendered it in Expanse in real time, and I think it looks pretty cool. All right, so I promised you that if you stuck around until the end of the tutorial, I would show you how to model Mars's atmosphere. So we're going to do that, and it's not going to take that long because we've already set everything up to make it possible. So the first thing that we're going to do is we are going to uncheck the rain fog and the ozone blocks because we won't need them. And we're also temporarily going to uncheck the aerosols block. And we're going to start, if we pull up a reference for Mars here, for one thing, we have this blue sunset, which is really cool. And it's got this kind of blue halo around the sun disk. So what that tells me is that that is anisotropic scattering happening. That's a directional phase function, right? And that's probably due to aerosols, some kind of dust particulates in the Martian atmosphere. So I know I'm going to want an aerosol layer that's similar to our aerosol layer on Earth, but that produces a blue color instead of just a gray color. And then the other thing that I notice here is that during the day the sky is kind of red, and it has this sort of like pale reddish brown sort of rusty color, right? And that looks to me like it might not be directional at all, or it might have a little bit of directionality, but not too much. So I'm just going to modify our air layer to mimic this color instead. Great. So I'm going to pop over to the air layer here. I'm going to call it Mars Air. And I am going to keep it as an exponential layer, I think. And I'm going to increase the thickness to something like 30,000, but then bring down the density to something like 0.1. And what this is going to do is that it's going to make the density sort of more uniform over the height of the atmosphere, but it's going to reduce the amount of total gas because I brought the density down. And this, I think, will make the Martian atmosphere look a little bit more uniformly, sort of that uniformly rust-colored, uniformly pale. And then I'm going to go over here to the scattering and extinction coefficients, and I'm going to make them kind of like a rust color. I kind of like that. And then maybe turn the saturation down to something like that. Yeah, that looks good. Great. And now I'm going to copy this color over to the extinction coefficients as well. And we might have to make an adjustment after we do that. Yeah. So now I'm going to up the saturation over on the scattering coefficients again. And I'm going to copy it back to the extinction. And the reason that I'm trying to keep these two the same is because real physical materials generally have the same extinction and scattering coefficients. So you're going to end up with a result that's a little bit more physical looking if you try and keep them as close to each other as possible. All right, let's just bump the saturation a little bit more and pull the hue a little more red. And now let's copy it back. Last one. Cool. Okay, so I think this looks pretty decent to me. I don't think it's perfect, but I think it's good enough for now. You could always tweak it more yourself and try and get it to look exactly how you want it to. The next thing I'm going to do, so I'm going to bring the sun down. I guess it's already relatively close to the horizon. It's somewhere around here. Yeah, so that's daytime. And then here, it's close to the horizon. And I'm gonna try and get that blue sunset color happening. So the way I'm gonna do that is I'm gonna go and I'm gonna turn our aerosols layer back on, and you're gonna see it's gonna look crazy, just because the atmosphere is much dimmer in general now. So this is just too much. So I'm gonna bring the density down to something like 0.5 maybe, and I think that looks pretty good. And now I'm just gonna give it a slight tint toward blue with the scattering coefficients. So I'm going to go over here. I'm just going to make it a little blue. And now to stay physical, I'm going to copy those back to the extinction coefficients. Cool. And then, I might actually, I'm going to reduce the anisotropy a little bit and up the density a little more. And then I think the other thing I'm going to do actually is I'm going to increase the thickness to something like maybe 3,000. And that'll make the halo a little taller. And now I'm going to bring the density back down to something like 0.75. And now you can see we sort of have our nice blue Martian sunset. It's a little bit, you get these sort of artifacts here when the sunset happens, but you can fix those by going over to the quality settings and upping the number of single scattering samples or upping the number of transmitted samples too, changing the quality, just making sure you capture the whole atmosphere. The Mirror's Edge version of Lower Manhattan on Mars. So there you have it, a Martian sunset, looking like it kind of does on the Curiosity rover videos. You can tweak this a little bit more. I'm sure you can get it to look even more accurate. But this will do for this tutorial. All right, so thanks everybody who stuck around this long. Thanks for watching the whole tutorial. I hope you enjoyed it. Just as a reminder, sort of a summary of what you learned. You learned about volumetric rendering and a little bit about atmospheric science, what the right way to render fluids is, and how to describe them statistically with the density field, scattering and extinction coefficients, and a phase function. Then we got into Unity, and we learned how to use atmosphere layer blocks with Expanse to set up a custom atmosphere. And we tweaked all of their parameters using reference photos as our guide to get the sky looking like how we want it to. Anyway, that is the end of the tutorial. There'll be more tutorials in the future. Maybe we'll do deeper dives on creating alien atmospheres. I have a clouds tutorial in the works right now that'll be up soon. But for now, I'll say thanks for watching, and I hope you have a great day.